everyone, and welcome to the third lesson of Fundamentals of Robotics. Today's lesson is about the degrees of freedom of the robot. We will become familiarized with the degrees of freedom of the robot, and we will find the general formula that we can find the degrees of freedom of any mechanism and not just the robotic arms. I'm Dr. Madison Babayaso, and I have a PhD in mechanical engineering. I worked mostly on robotics and mechatronics projects during my master's and PhD work. Okay, without further ado, let's get started. Degrees of freedom of a robot is the dimension of the C-space of the robot, which in turn is the minimum number of the real numbers that are needed to represent the C-space of the robot. We saw in the previous video that the configuration of the robot is the answer to the question, where is the robot? And we saw different ways to represent the C-space of the robot. So the degrees of freedom of the robot is the minimum number, a real number, that is needed to represent the configuration of the robot, or the C-space, or the configuration space of the robot. A rigid body in 3D space has 6 degrees of freedom. So suppose that this is X coordinate, Y coordinate, and Z coordinate. So the rigid body has 6 degrees of freedom. The motion along the X-axis, the motion along the Y-axis, and the motion along the Z-axis. These are 3 translational degrees of freedom. It also has 3 rotational degrees of freedom. Rotation around the X, rotation around the Y, and rotation around the Z-axis. So overall, it has 6 degrees of freedom, 3 for orientation, and 3 for position. You can also imagine this by taking 3 points on the rigid body. For the first point, there are 3 freedoms, X, Y, and Z, and there is no constraints. For the second point, we know that the distance between 2 points on the rigid body should be constant. So B can only be on the surface of a sphere with center at A, and this gives us 2 rotational degrees of freedom. In other words, 3 coordinates for B minus 1 independent constraint is 2 real freedoms. For the third point, the distance of this point to A and B should be constant. So C can only be on the circle of the intersection of 2 spheres, and this gives us 1 rotational degrees of freedom. In other words, with 3 coordinates for C and 2 independent constraints, we have only 1 degrees of freedom. For point D and so on, the position of the point is fully determined, and there is no more freedoms in choosing the place of those points. With the same analogy, we can say that rigid body on 2D plane has 3 degrees of freedom, 2 linear degrees of freedom, and 1 rotational degrees of freedom. Suppose we have this rigid body on plane, this toy car in the plane, with X-axis and Y-axis. Okay? X-axis, Y-axis, and Z-axis. As we saw, a rigid body in 3D space has 6 degrees of freedom. So if we confine a rigid body to the plane, to this plane, we will impose 3 constraints on it. It cannot move in Z direction because it's confined on the plane, and it cannot rotate around the X or Y axes. And this means that there will be no roll and pitch angles. So we will have 3 degrees of freedom. You can also take 3 points on the rigid body. So the degrees of freedom that we have for the first point is 2, okay, X and Y, and there is no constraints. The second point will be at the circle centered at the first point, and the location of the third point will be fully determined. So a rigid body in plane has 3 degrees of freedom. Now think about the rigid body in 4-dimensional space. How many degrees of freedom does a rigid body in 4-dimensional space have? How many degrees of freedom are rotational and how many are translational. Think about it. We have seen that a rigid body in 2D space has 3 degrees of freedom. 1 rotational degrees of freedom and 2 translational degrees of freedom. But why does this robot with 2 links and 2 joints, it has 2 rigid bodies, it has only 2 degrees of freedom, but not 3? Each link doesn't have 3 degrees of freedom. The answer lies in the number of constraints that each of the joints put on the motion of the links. So for instance, in this 2-dimensional planar robot, each rotational joint puts 2 constraints on the motion of the link. So the link cannot move in the X or Y direction. It only can rotate around the Z axis. So it only has 1 degree of freedom. So each joint provides 1 degree of freedom. So the overall has 2 degrees of freedom. So we should be careful when deciding about the number of degrees of freedom of a mechanism, because the joints puts constraints on the motion of the links or the rigid body. If we imagine a robot in 3 dimension as the 3R robot in this video that has 3 Revolute joints, these 3 Revolute joints are apart from the end effector of the robot. The Revolute joint will put 5 constraints on the motion of 1 link with respect to the other link. So again, it will provide only 1 degree of freedom. So this 3R robot will have 3 degrees of freedom other than its end effector because it has 3 rotational joints. So up to this point, we've learned that the constraints on the links come from the joints. So now let's see how many different joints are used in different kinds of robots. A Revolute joint, as we saw in the industrial robot of the previous video, is like a door hinge. It provides 1 degree of freedom of motion between 2 bodies that it connects. The rotation is around the joint axis, and the positive rotation can be determined using the right-hand rule. To the right-hand rule, if your thumb is in the direction of the rotation axis, the positive rotation is the direction where your forefingers curl. A linear, sliding, or prismatic joint provides the linear motion between 2 links. It will again provide only 1 degree of freedom between 2 links. The robot in the picture has 3 prismatic joints, so it has 3 linear degrees of freedom. Next is the universal joint, which is 2 rotational joints that are orthogonal to each other. So it can provide 2 rotational degrees of freedom. These 2 rotational degrees of freedom are around the roll and pitch axis that are X and Y axes. The spherical, or we call it shoulder joint or ball and socket joint, is the same as this universal joint, but it also has another degrees of freedom, the rotation around its axis. So it has the 2 degrees of freedom of the universal joint plus the rotation around the axis of the joint. Next is the cylindrical joint that can provide independent translation and rotation around the single fixed joint axis. So it can provide us with 2 degrees of freedom. And the final joint that we want to talk about is the helical or screw joint that can provide a simultaneous translation and rotation around the screw axis. So it has only 1 degree of freedom. The difference between this joint and the cylindrical joint that we just saw is that the cylindrical joint can provide independent rotation and translation around the joint axis, but helical joint provides simultaneous rotation and translation around the joint axis. So it only provides us with 1 degree of freedom. Now let's talk about the Grübler's formula. Grübler's formula is a general formula that we can find the degrees of freedom of any mechanism. It's not just applicable to robots. Grübler's formula states that the degrees of freedom of a mechanism is equal to the sum of the degrees of freedom of its bodies minus the total number of the independent constraints put on the motion of those bodies. If we take n as the number of links, note that traditionally we also take the ground as one of our links. And if j is the number of the joints, and if m is the number of degrees of freedom of a single body, that is 6 for the spatial bodies and 3 for the planar bodies, we can write the degrees of freedom equal to the freedom of the bodies minus the number of the constraints. Note that we deduct 1 from the n because we want to exclude the ground. We have seen in the 2DOF planar robot example that the degree of freedom of the movement of one link with respect to the other can be found by deducting the number of constraints that the joint puts on the movement of that link from the degrees of freedom of a rigid body. Writing the Grübler's formula in terms of the degrees of freedom of the links, we can find this formula, and it can be used to find the degrees of freedom of any mechanism. Remember that all constraints are independent. Now let's see some examples. We saw before that our 2DOF planar robot has 2 degrees of freedom. Now let's see if we can get the same answer with the Grübler's formula. So for the 2DOF planar robot, the m is equal to 3 because it's a planar rigid body. So the rigid body in a plane has 3 degrees of freedom. The robot has 3 links. Remember that? The ground is also a link. We have 2 joints, joint 1 and joint 2. And the sum of the degrees of freedom of the joints are 2. Each joint provides us with 1 degrees of freedom. So using the Grübler's formula, we can see that the 2DOF planar robot has 2 degrees of freedom. Now, let's step it up a notch and find the degrees of freedom of a 4-bar linkage. M is equal to 3 because it's a planar robot. We have 4 links because, remember, we take the ground as one of our links too. We have 4 joints, and the sum of the degrees of freedom of the joints is 4 because each rotational joint can provide us with 1 degrees of freedom. Using Grübler's formula, we can see that it has only 1 degrees of freedom. We could also expect this result because suppose that the 4-bar linkage is a 3R open chain robot, that the 2 ends are pinned. So the 3R open chain robot, as we saw before, has 3 degrees of freedom. So 3 DOF of the serial chain minus 2 constraints gives us 1 degrees of freedom. I reiterate that for the Grübler's formula to work, all the constraints must be independent. Now let's go ahead and see some spatial robots. The first mechanism is a Stewart mechanism, which is a parallel mechanism with 6 legs. Each leg has 2 spherical joints and 1 prismatic joint. We can also replace the bottom spherical joints with universal joints with 2 degrees of freedom. Because it's a parallel robot, each leg supports a fraction of the weight of the payload. Now let's find the degrees of freedom of the robot. M is equal to 6 because it's a spatial robot, and a spatial rigid body has 6 degrees of freedom. It has 14 links because we have 2 platforms, top platform and the bottom platform, that provides 2 links, and each leg has 2 links. So 6 times 2 is the total number of the links of the legs. So it has 14 links in total. It has 18 joints because each leg has 3 joints. So 6 times 3 is equal to 18. And each leg has 7 degrees of freedom. So overall, it has 42 degrees of freedom for the joints. So using Grübler's formula, the degrees of freedom of a Stewart platform is 12. Of these 12 degrees of freedom, only 6 degrees of freedom are shown in the top platform, since the other 6 are torsional rotations about the leg axis. So do you remember that the spherical joints have 3 degrees of freedom, which one of them is rotation around the joint axis? So there would be 6 degrees of freedom for the torsional rotations of the legs. And they have no effect on the motion of the mobile platform. Because the top platform can move with full 6 degrees of freedom of a rigid body in space, the Stewart platform is usually used to simulate airplanes. This video shows the Stewart platform in action. The top platform can move with 6 degrees of freedom of a rigid body. Now let's find the degrees of freedom of a delta robot. Delta robot is a parallel robot that can maintain the orientation of its end effector, unlike the Stewart platform that can change the orientation of its end effector. Now let's calculate the degrees of freedom of the robot. It has 3 legs, and each leg has 3 revolute joints, 4 spherical joints, and 5 links. Thus, we know that m is equal to 3 because a rigid body in space has 6 degrees of freedom. It has 17 links because each of the legs has 5 links, so 3 times 5 plus 2 platforms is 17. It has 21 joints because each leg has 7 joints. The 3 times 7 is equal to 21. And the sum of the degrees of freedom of the joints is 45 because each leg has 15 degrees of freedom. So using Grübler's formula, we can find that the delta robot has 15 degrees of freedom. But of these 15 degrees of freedom, 12 are related to torsion of the 12 links because of being connected to the spherical joints. These degrees of freedom are called internal degrees of freedom. Only 3 are visible at the end effector and the moving platform. Delta robot acts as an XYZ Cartesian positioning device. This video also shows that only 3 out of 15 degrees of freedom are visible at the end effector, and delta robot is like an XYZ Cartesian positioning device. Let's see another example. Consider a 7 degrees of freedom robot arm that mimics the 7 degrees of freedom of the human arm. As you can see, 3 rotational degrees of freedom for the shoulder joint, 1 rotational degrees of freedom for the elbow, and 3 rotational degrees of freedom for the wrist. And assume that this robot should carry a tray with drinks on it. The drinks shouldn't be spilled from the tray. How many degrees of freedom does the robot arm have while satisfying this constraint? Here's a cool video of the Simo robot serving food for the customers and carrying a tray. You can see that he carries the food without spilling it, satisfying all the constraints. Now let's solve a fun problem. Suppose that my arm is a 7 degrees of freedom robot arm. 3 degrees of freedom for my shoulder joint. It's a ball and socket joint, right? 1 degrees of freedom for my elbow joint. It's a rotary joint, right? And 3 degrees of freedom for my wrist joint. So overall, the arm, without, if you don't take into consideration the fingers, it has 7 degrees of freedom. So now let's suppose that I'm a robot, okay? So suppose that I should, the robot, not me, the robot should be specified a task that the robot should carry a tray with drinks on it. The robot shouldn't spill the drinks. So how many degrees of freedom the robot arm now have if we put that constraint that the robot arm shouldn't spill the drinks. So the constraint that I put on the robot arm states that the drinks shouldn't be spilled. So if the robot rotates it around the x-axis, they would spill. So no rotation around the roll. If the robot tries to rotate around the y-axis or the roll, or the pitch axis, the drinks will spill again. So we have two constraints. The robot cannot rotate the drinks around the x-axis. It also cannot rotate the drinks around the y-axis. So we put two constraints. It can move in this way, in this way, in the z-axis, and it can rotate in the z direction, but it cannot rotate in the x and y direction. So the robot arm with these two constraints would have 5 DOFs. Well, that's going to wrap up today's lesson. Thank you everyone for watching, and I hope you enjoyed this video. And I hope you also get a good understanding of the degrees of freedom of the robot, and also the Grübler's formula to find the degrees of freedom of the mechanisms, and especially the robots. I hope to see you in the next lesson. Bye-bye.